Hi everyone, my name is Angeli Sandoval, and I'm a master's student at the CUNY Graduate Center, and I'm a research affiliate at NASA Goddard Space Flight Center, and today I'll be talking a little bit about a thesis project I've been working on, which is tentatively titled Refining Orbits and Revealing Origins, a study of giant exoplanets around low-mass stars, under the guidance of Dr. Nicole Colon and Dr. Caleb Gañas. So to start, what are exoplanets and why are they important? Exoplanets are planets beyond our solar system, and we detect them primarily using two methods. One of them is the radial velocity method, and the other is the transit method. And to date, we've detected over 5,000 exoplanets using different observational facilities. And understanding exoplanets are important because they can help us better understand planet formation and our place in the universe. So, like I mentioned earlier, there are two ways we detect them, and the GIF on the left is supposed to be a GIF. Is a technique, is a transit method, which is a technique that looks for small regular dips in the star's brightness. So when the planet passes in front of the star, and if the GIF was working, then you'd see that there would be a dip right there at the center. And it happens when the planet passes in front of the star. Sort of like a mini eclipse. And from this, we can figure out the planet's size, how long it takes to orbit, and how deep the dip is. Our data that we obtained was from NASA Kepler and the test missions. And on the right, we have the radial velocity method, and that measures a tiny wobble of a star caused by the gravitational pull of an orbiting planet. And we detect this wobble through shifts in the star's light, known as Doppler shifts. This can tell us the planet's mass and helps us confirm whether a signal from the transit method is truly caused by the planet. And the data that we used is from the spectrographs HPF, NUID, and MaroonX. So there are several types of exoplanets, which are terrestrials, super-Earths, Neptunians, and gas giants. My work focuses on the gas giants on the last group, which are Jupiter or Saturn-sized planets composed of mainly hydrogen and helium with no solid surfaces, and they're often found close to their host stars. So why gas giants are on M-dwarfs? They're interesting because their information around low-mass M-dwarfs is unexpected. These stars have lower disk masses, making it harder to form large planets, yet we continue to find them. Their large size relative to the host star makes them easier to detect and can serve as good targets for atmospheric studies. And the questions we are trying to answer are, how do these small stars form such large planets? And I try to answer these questions with the GEM survey. So the GEM survey is a research project dedicated to discovering and studying gas giant planets orbiting these M-dwarfs. And these stars are relatively cool, less than 4,000 Kelvin. And the planets in the survey are quite large, about 8 to 15 times the Earth's radius, or 80 times the Earth's mass. And so far, we've confirmed about 30 GEMs. And understanding them helps us test ideas about how planets form in environments very different from our own solar system. So to study these gas giants around the M-dwarfs, I developed a pipeline and first looked at the system EPIC 212, 813, 907. And this system was first discovered by NASA's K2 mission. And what's special about this star system is that it hosts two giant planets, one that orbits very close to its star, known as a hot Jupiter, and completes an orbit about 6.7 days. And the second is much further out and is considered a cold Jupiter, whose exact orbit we're not entirely sure about, but it takes roughly at least 800 days to orbit the star. So first, I clean and prepare the raw observational data using software tools designed for exoplanet analysis. I use mathematical models to help us precisely measure the planet's size, orbit, and other important characteristics. And this approach allows us to separate the planet's signal from the natural variability of the star. And the ultimate goal here is to clearly understand these planets' orbits and properties and set the stage for the main star of the show, which is the system that I mainly study, TOI 5349. Okay, so TOI 5349 is a system orbiting, containing an M dwarf that is approximately 9 billion years old, has an effective temperature of 3751 Kelvin, and a metallicity of 0.50 dex, which I'll come back to later because it's important for understanding how planets form. And after running the pipeline, we determined some of the planet's basic properties, such that it completes an orbit every 3.3 days, meaning that it's very close to a star. It has a radius of 0.91 Jupiter radii, and it has a mass about 40% of the mass of Jupiter, and makes, we can calculate a low overall density of 0.66 grams per cubic centimeter, which is, we found to be close to Saturn's density. So the bottom left plot is data from TOI 5349 and obtained from the NASA test mission. And it's showing the light curve and the best fit model noted by the orange line. And on the right, we have the radial velocity data from the spectrographs I mentioned earlier. And again, we have the best fit model indicated by the orange line. Okay, so here we're comparing the mass and size of our main planet of interest, TOI 5349, with other planets in the GEM survey. Each line in the plot represents a different planet density, or how compactly the planet's material is indicated by the gray dashed line. And we have Saturn and Jupiter for reference by the planet icons. And we can see that many of the GEM's planets, including TOI 5349b, indicated by the star icon, has densities very similar to Saturn's, suggesting that these planets might be failed Jupiters. And what I mean by that is that they started forming large cores, but stopped at some point gathering gas before reaching Jupiter-like sizes. And again, we're comparing TOI 5349 to other GEMS planets, but now we're looking at their density versus the metallicity of their host star. And metallicity refers to how rich a star is in metals, heavier elements beyond hydrogen and helium. This plot shows a clear relationship where lower density planets like TOI 5349b tend to orbit very metal-rich stars. The bar graph below confirms that gas giants prefer these metal-rich environments, and this supports the idea that metal-rich stars help quickly form large planet cores, but prevent them from fully becoming Jupiter-sized planets. So what did we learn? Giant planets orbiting small stars like M dwarfs are rare, but they teach us a lot. Systems like EPIC 212 and TOI 5349b showcase different planet arrangements. And high star metallicity seems important for forming these intermediate-sized failed Jupiters. I think my research contributes to precisely measuring these planets and understanding their formation. And for future work, we plan to gather more data, possibly keep studying EPIC 212. It's better understanding the orbit of the second planet. Share the discovery. I'm currently working on publishing the results for TOI 5349b, and maybe later on we can explore more trends on the all of the GEMS planets that we found so far. And lastly, I just want to acknowledge and thank the CUNY Master's Program and Simons Foundation for making this work possible, along with my advisors, Nicole, Caleb, and Lucia. And finally, I also want to thank my cohort and partner, Merlin, for their undying support in getting me through this past couple of years. Thank you.
Thanks so much. That was amazingly fascinating. I'm still trying to wrap my head around the results that you got, where you kind of have these sort of smaller hot Jupiters around M dwarfs. And I'm wondering if you can describe whether that's as surprising. Should I be as surprised as I am? I don't know why I'm surprised, but I just kind of was like, that seems Not something I was necessarily expecting. Were you surprised? Were other people surprised by this? And can you speak
I
to that?
I think I was initially surprised, but I will say that after I read like a bunch of papers, um, I guess it makes sense in the way that I think so. When Jupiter's forming, there's this process called like runaway gas accretion, and it just gains a bunch of gas and gets to the size that it is. But for some reason, the M dwarfs and has a lot of metals in an environment, and so when these planets are forming around these metal-rich M dwarfs, the metallicity sort of impedes that runaway gas accretion to form those Jupiter-sized planets. And so this is what we're finding now. It's still preliminary, but yeah.
So great work.
Thank you.
I was surprised, I guess I just didn't know it, that gas giants around M dwarfs were so rare. And this might be something you haven't looked at, is Proxima b in that category?
No, I don't believe so.
Yeah, because it's never clear if that's actually a gas giant or Neptunian.
Yeah, well, from what I looked at, I don't remember that star. The survey has very specific criteria, so what will make the cut. So I'm assuming that probably didn't make the cut. Yeah.
Oh, that's right. No transit, yeah.
Yeah.
All right, well, let's thank Angeli.